Okay, so for those who missed yesterday, a quick recap of what we did. So we looked at the difference between n log n and n square could be a difference of something like when n is very large. That's just to illustrate. Later on in the course, we will be talking about polynomial time algorithm versus exponential time algorithm, but this tells you that at least between n log n and n square, there is a huge difference as n increases. This is one thing we saw did some calculations and verified this. Along the way, we also revised some basic sorting, searching algorithms and some data structures. So the point is that these are some of the things we will not cover in this course. We assume that you know some basic sorting algorithms, searching algorithms, basic data structures, basic graph algorithms. So this will be like, sort of like algorithm 1.5 kind of course. Okay? So slightly advanced, because that's sort of the background of all of you as well as all of them. So then we actually saw this notion of amortized complexity. So this was the new topic we started on. Okay. So you've seen worst case complexity of algorithms. You've seen probably even average case. Amortized complexity is an important measure, especially when we are looking at operations on data structure. Particularly on data structure queries. Sometimes when you implement them in algorithms, you may not necessarily care about the time for one query, but you care about the time for a sequence of queries. So one or two queries in this sequence may take more time. If that enables certain cheaper, faster query later, then we will allow that. So I didn't formally define it, but let me try now. So amortized cost of some operation, right? Some query, insertion, deletion, something on a data structure can be defined like this. Max over all sequence involving this operation. Call the sequence S. Total time for S divided by the length. Okay. So it is sort of an average time, but there is no randomization, no distribution happening. But you take a sequence of operations, take the total time and divide by the length of the sequence. And that is the amortized cost of the operation. And we do this over all possible sequences. Okay. So clearly, if your query has worst case complexity of something, let's say worst case is some k, then this would be at most k times kernel k raised by kernel k. Yeah? So it's at most k. Clearly, amortized cost would be less than the worst case. But there are examples where we saw last time, I'll just recap that, where the amortized cost is actually considerably smaller than the worst case. Okay. So the example we saw was incrementing a binary counter. So what is this? So you have a k-bit counter, and the algorithm we want to just say increment. Okay, simple enough. So the counter will be like 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, and I want to increment. So the simple algorithm is you start from the right, skip all the ones, change them to 0 until you come to a 0, change it to 1. Right? Standard. The worst case, it could take k bit flips, but what we analyzed is, suppose I start with all zeros and perform a sequence of increments, some n such increments, then how much time does it take for the overall thing? Because then that by the length of the sequence will give you the amortized cost. Okay. So what did we see that was? For binary increment 2. So what we saw was that the amortized cost of a binary increment is actually only 2, even though in the worst case it takes 3. Which means that you start from 0, 0, 0, 0 and do a whole bunch of, say, let's say 10,000 increments, then the total time is never more than 2 times 10,000. It's not k times 10,000, but it's at most 2 times. Okay, so here is a simple intuitive, there are a couple of ways in which we analyzed it, and today I'll do another example where you will understand this. So one simple way we analyze is how many times will the last bit be flipped in my, suppose I do n increment. Start with 0, 0, 0, 0 and do some n increment. How many times will the last bit be flipped? All the time, right? So n times. How many times the second last bit will be flipped? N by 2 times. Right? Because whenever the last bit is 0, you will flip it to 1 and be done with it. So, and that happens half the time. If you are starting with 0, 0 and you are doing 0. So, the second last bit will be flipped n by 2 times, third last bit will be flipped n by 4 times, and if you sum them all, it's a geometric series, that sum is 2n. Okay? And we also came up with this potential argument, which is what we need for some, when we do this more complex data structures. And using that also, we argued that amortized cost is 2. Okay. So before I get onto the next example, suppose I also do some decrements in between. What happens? So now I'm not doing a sequence of just increments. I'm doing some increments followed by some decrements, followed by increments, followed by decrements. Then will our analysis hold true? Is it still constant amortized time, or what do you say? So what was the intuition for constant amortized cost? Okay, let me just explain you the other thing. What we did is that, if you are doing, suppose my one increment performed some L flip operations, that means what? It was like this. And then after that, the new number becomes something like this, right? Whatever it was. So in particular, the new number had a lots of zeros, which is a good thing, because when you have zeros, the algorithm doesn't have to do much. Just changes it to 1 and be done. So this is how. So the whole challenge in doing this amortized analysis is there are some interrelationship between the operations and how do you capture them, right? So this expensive operation doesn't happen very often. How long does it take for such an expensive operation to come again? You have to do so many increments before you get to such an expensive operation. So you amortize the cost of the expensive operation to these cheap operations. So we somehow distribute the cost and say, oh, this is going to take a long time, but that's going to happen not very often. So by the time you get there, so many other increments have done. So I will sort of distribute the cost to them. Okay, that's the idea. And I can do an increment, decrement. Every operation is expensive. It's going to take that much time. So, for example, I can come up with a sequence of increment operations, right? So I start with, starting with 0, 0, 0, I'll do increment. Let's say I do it some 2 power. So it's a k bit counter. Let's say I do it 2 power k by 2 minus 1 times. Okay. So eventually, after that, I will have 1, 1, 1, 1, 1, 1, 1, something like this. Some k by 2 ones. Then after that, I do increment, decrement, increment, decrement forever. Each of this is going to cost you k, right? So it's true that initially there will be some cheap operations, inexpensive operations, but this is over for any sequence, right? So now I can have a very long sequence which offsets the inexpensive cost initially, so that these costs will start dominating, and so the cost will be omega k, right? It's not constant. So this is important, right? That if I also interburst with some decrement operations, whatever we did, not only the analysis breaks down, we can come up with an example to show that there is a sequence where the total time would be k times the number of operations, or some function of k times the number of operations in the sequence, right? So this is also another way to show an amortized complexity is actually large. How do you show? Right? To show that amortized complexity is small, we have a couple of ways of analyzing it. We did, and we will do another example. But if I want to show that an amortized complexity of some operation is large, you come up with a sequence of operations where the total time is very large. Right? So here is a sequence where I start with, I have to build up muscle to get some k by 2 number of ones, and after that I'm going to do increment. Each one is going to take some k by 2. Right? So this initially may be inexpensive, but I can make this sequence arbitrarily large so that these costs start dominating. So the overall cost would be omega k. Right? I have to make sure you know these notations, right? You understand what this is. Okay, so good. So this tells you that whatever we did works. I'm just doing increments. But if you want to do decrements, then that bet is off. Alright, so other example which I want to do is you want to implement a stack. But now we have the standard stack operations are push x onto the set S, pop S, whatever the top element of this stack. I'm going to introduce another operation, multiforme, which means that pop the top k elements of the set. Okay, but stack may not have k elements. K is some integer, let's say, some fixed, some large number. So if stack does not have k elements, then you pop whatever number of elements is there. Okay, so the size of the stack is less than k, then delete everything from the stack. If it's more than k, delete the top k elements of the stack. Okay, so how would you implement it, and what are the worst case complexity of these operations? How do you implement a stack? Generally, use an array or a linked list or something. You just have to have a pointer at the head of the linked list, and so the push and pop will take some constant time. You just have to go to that pop and move it, or move that pointer right direction or left direction. And multi-pop will take time, k in the worst case. So now the question is, starting from an empty stack, I perform n push pop or multi-pop operations. How much time will that take overall? Again, in the worst case, trivially it's at most most what? And k, right? Because worst case, any of them takes k. So if I'm unlucky and I'm just doing a lot of multi-pop operations, it might take n times k. But can you say something better than that?
Only we can pop only those many number of elements that we have put it into this.
Okay, so
the
observation is that you can pop only if you're pushed. So total time yes, so let's say there is some constant time for each of these operations. Some constant here, some constant here, here it's actually minimum of this. Yes. So what is the next step of your group? You can pop only if you can push. So what will be the total time? Or let's say the total number of elements popped is at most
the total number of elements
pushed, right? Total number of elements pushed, popped. Right? So I want to just say that this is at most, I'm going to have a constant, 1 unit for each one of them. Yeah? N by 2. Okay. So I'm going to have a 1 unit for every operation anyway if I'm doing n sequences. Plus I want to say it's the number of pushes. So it depends on what I mean by time. Okay. So let's say the time for this operation is 1, time for this operation is 1, and time for this operation is 1 plus minimum of some 1 unit to go and do something there, plus then I am adding all this and saying that's n plus this number over all this sequence will be at most the number of pushes, which I know is at most n, so that's at most 2n. Okay, this is sort of an aggregate way of analyzing this. This is like the way in the increment algorithm we said the last bit is incremented at more all the time, the previous bit and so on. But then we also saw some potential, some credit-based way of analyzing this. So how do you come up with credit? So if I say that, so recall what was the credit-based analysis for the increment operation? Think of it as every operation comes with some credit, some charge, okay? And it's going to use the charge to pay for the operation, whatever the cost. But if it actually takes less time than what the charge it is bringing, it's going to keep the extra amount in the data structure for some expensive operation to use it. Similarly, if it needs more, it is going to borrow from the structure and use it. And the way you have to come up with enough charges so that there is always enough for an expensive operation to gather it from there, right? And so for the increment operation, we said it's enough if every operation comes with 2 units charge, which it's going to use. How was it using the 2 units? Do you remember? So for the increment operation, the operation will actually come with 2 units of charge. How is it using?
1 unit for the 0 to 1 flip, and the leftover is based on the 1.
Exactly. So the 2 units are used for, remember, every increment operation performs exactly 1 0 to 1 flip, right? Because there are lots. So 1 0 flip followed by a 0 to 1 flip. So it will pay for the 0 to 1 flip and put a charge of 1 credit on the 1 it has created. Okay? But who is going to pay for the 1 0 flips? The previous operations have paid for it because they all kept a charge of 1 1 unit there. So we use this is what I meant by this over counting of the running time, right? So we sort of did some over counting. How much over counting we have done is how many ones are there, right? So now this is an expensive operation. So 1 0 flips it's going to use from the credit there already, and so 0 1 flip it will pay for it, and for the one it has created, it will put a charge of 1. Okay. So similarly, if I want to use some sort of a charging operation, how much charge do you want to give for the push operation, how much for the pop, and how much for the multi? Two for push operation. How do we distribute that cost?
One for performing the operation and one on the element.
Exactly. So one for performing the operation, one on the element. And how much charge you're going to give it for pop? Nothing. That you are popping the top element. That element already has a charge. I already counted it for the push, so I'm going to use that to remove it. Similarly, multi-pop will take all the charges in there, right? So what would be the potential of the data structure?
Number of elements.
Exactly, right? So this is how we sort of progressed. We had an overall analysis which gave some sort of an intuition about this charging argument, which gave what the potential of the data structure should be. After that, we had some formula which just gave us what is the amortized cost, right? So so the potential of my data structure is the stack. Is the number of elements in the stack. So roughly what it captures is the amount of credit in the stack. Amount of credit already sitting in the data structure. This is the amount of over counting I have done on the running time, so that an expensive operation can use this, right? So then if I do that, then here is just a formula. Very soon when we get to some data structures, I'll just define the potential, we'll plug it into the formula and compute the amortized cost. So amortized cost of whatever operation, in this case it will be any of these three operations, let's call this the ith operation, would be whatever is actual cost is less what happens to the data structure after this operation minus, right? So this is DI is SRH. S after this current operation, and Si minus 1 is S before. This is after the other. And the reason this is amortized cost is because, remember, my interest is the total cost. If I sum this, sum of the amortized cost, the way I arrived at this formula is actually sum of the actual cost plus the potential at the end minus the potential at the beginning. Okay. If the potential is defined as it's always greater than or equal to 0, then I would ignore the potential at the end. Okay, so the sum of the actual cost and this is my interest. All I care about total actual cost for this sequence, right? Amortized cost is some formula I'm going to plug it in and get something, but I know from this formula that it's summation amortized cost plus because there is a telescopic sum, and this is less than or equal to summation amortized cost plus. Typically, we know what phi of D naught is because this is the structure we started off with, and we defined the potential so we can compute it. The amortized cost is computed like this nicely using this formula. So what we have is that if you use this formula to compute the amortized cost, then the total, multiplied by the number of sequences you have, number of operations in the sequence, then that gives you an upper bound for the summation actual. Okay. Instead of just simply saying n times the worst case cost, which could be a huge overestimate, we have a much tighter estimate. Okay. So now let's plug it in for our operation. So if I want to do the push operation, what is the amortized cost of push? Because it should match with this intuition of what each operation is coming with, right? So amortized cost of push is, what is the actual cost? 1 unit, whatever that constant is, plus what happens to the potential difference? It increases by 1, right? Because potential is the number of elements in the stack. So this is 2. What is the amortized cost of 1 unit for the operation? And it decreases by 1. And similarly, if the amortized cost of multiforme, I don't know what the actual cost is. It could be some L, because that may not be full. Okay. But if it spends that much, the potential drops by L. Okay. So now if I want to know what is the total cost for a sequence of push, pop, multi-pop operations, it's 2 into number of push operations. That's it. It may not have matched with my 1 unit cost, so you may have to add a 1 there. Okay, so what is the story? That somehow this charging argument gives a way of connecting this expensive operation with cheap operation, and it gives you an idea of this potential, and you can just plug it into this formula to get a model. Okay, and this is also the way we did the binary increment analysis. So what was the potential there when we are doing the increment of the counter? Number of ones in your sequence, because there was a credit with every one. Okay, good. Okay, so now let me just get to a little more involved example where, and this is actually used in practice, which is the dynamic array or hash table or something. So what is this? So you're trying to support insert and delete. Let's for now just say insert operation. You're just building some dictionary, your elements are coming and you are inserting it and maybe using some sort of a hashing. Okay. But you don't know how many elements are going to come. So, and you don't want to waste a lot of space. Okay. So you want to create this space dynamically. So I'll create an array of certain size and keep hashing it into that array. Now when the array gets full, I need to do something because I need to insert the next element. And I'm not just going to add an extra location because this hash table needs to be hashed completely. It depends on the size of the table and so on. So what I would ask my operating system is to create another table of some size larger than this current size and copy all elements there using my old hash algorithm or whatever. Okay. So there is a trade-off between, I don't want to waste too much space because if I don't care about too much space, initially itself I can ask my table to be as large as possible, and that may be good enough to insert everybody, but that may be wasting a lot of space. And I want to minimize my time also, because if I have very little space, then for every insertion I'm going to ask for another array and copy everybody and spend a lot of time. Okay. So what we're going to do is, so there is a basic insert operation, which given an element, it will just go and insert it in some table, constant time. That's the assumption it will take. And then there is this, let's call this, I don't know what they call it, a table insert where which algorithm will look like this. Do basic insert if there is space. If not, create a table of double the size and copy all elements into that new table. Okay, so to start, and what is the goal? Keep empty slots to be this is all English, but I formalize things, but hopefully it's clear that I don't want too much empty slot in my table size, which means I don't want the table size to be too large compared to the number of elements present there. So whenever table is full, I'm going to get double the size and copy all the elements. And then the subsequent inserts will be very easy because up to a point there I'll just keep inserting it. Again the table will get filled and then I will double the size and I keep doing it. So suppose I do a sequence of such table insert operations, I want to understand how much time it might take in the worst case for the whole sequence. So total time. This is what I'm interested in. Okay? So, and the way I'm going to count is how many basic inserts are happening. Right? So let's just simulate. So suppose to start with, I will get a table of size 1. I insert somebody there. And the new element comes. There is no space, so I'm going to get double the space. And then the new element comes. I don't have space. I'm going to get a table of size 4. I mean, x1, x2 may not actually go in this location. Some hash function will somehow distribute it, right? So I'm going to insert maybe x3 here because that's what the hash function. The basic insert is some data structure. Insert example, hashing, I don't care, but all I'm going to assume is that it takes constant time. If you give an element and give the table size, it will just insert you into some location, some empty location. It will insert it in empty location. So now x4 comes, I'm going to insert it here. But when x5 comes, I will have a table of location 1, 8. All these guys are copied into that. And then the next 4 insertions will be cheap. I'll insert them. And when x9 comes, I will double the table, keep inserting it. Now I want to know what is the total cost for if I do this n big insertions. Okay. This is actually implemented in practice in hash tables and so on because you want to make sure that your space wastage is not much and you don't know the size of the data. So this is how you will dynamically insert. So what can be the worst case time here? If I'm doing some insertion, maybe the last insertion copies everybody into this new table, so it could be as bad as n. But for the whole sequence, the worst case for any query could be n, the worst case could be n squared, but will it be n squared? What will be the amortized complex? When? So here in this case, we actually know the cost of the ith operation. So let's actually do that, right? Let's compute it. What is the cost of the first operation? Let's suppose Ci, the cost of ith operation, right? So C1 is 1, right? I'm just inserting it here. C2 would be 2, right? Because it's just one insertion, but the table is full. So I have to create a new table, copy x1 and then insert x2. What about C3? 3, right? Because again I create a table, copy these two plus insert this, so that's 3. C4 would be 1 because there is an empty spot available. Good. C5 would be 5. C6 1, C7 would be 1, C8 would be 1, and then C9 would be 9. So what is the pattern here? When is it 1 and when is it? So basically it's 1 or I. If you look at the pattern, Ci is either 1 or I. When is it I?
2 power I. 2 power I plus 1. The operation is always I.
So Ci is equal to I if something happens. One otherwise. When is it I?
Excavation has 2 power k plus 6.
Okay.
I is.
Okay, that's a nicer way of saying it. If I minus 1 is a power of. Okay, so it's not magic. We actually know the cost of every operation. Let's sum this and see what happens, right? Because there's reasonable enough thing. So what is summation Ci? If I do n such operations, so I hope the algorithm is clear. What we are doing, this table insertion, right? We went through. So what is this? So I'm going to say it's n plus. So I write this as 1 plus I minus 1. Okay? So this 1 and this 1 is accounted for n. Then what I have is some powers of 2. Right? Because these I minus 1s are powers of 2. Some 2 power k going from for all k 0 to 0 log n. Log n minus 1, starting with 0, 1, whatever. Right? But can you say what it is? What is it? Some upper bound. 2n. Okay? This is geometric series, right? So this is going to be very useful. We're going to keep encountering this. We did encounter it yesterday. Right? 1 plus half plus 1 by 4 plus 1 by 8, and if you sum all the way, it's 2. So it's basically that times n. Okay? So this is the last term is n, not ceiling, maybe floor, I'll say. So n plus n by 2 plus n by 4, that's what's happening. Even if you go all the way, it's 2n. So this is at least 3. Okay, so this is sort of an aggregate way of analyzing it. Let's think of potential and charging argument. So this tells you somehow that I want every operation to come with the credit of 3 units of time. How is it going to pay for it? And why 3? Okay. So let's think about when do we really need a lot of charge on the table?
No, I don't use two operations. Insert and copy.
So when do we need a lot of charge on the table, right? So when the table gets filled up, I will create a table of double the size. I want the picture to reflect. And I create a table of double the size, and it will be half full at that time, right? Because all these guys will be copied.
So does creating table involve any cost?
No. I mean, you can add a unit cost if you want, but no. We are only going to count in terms of this basic insert operation. That is our measure. How many simple inserts you are doing. Okay. So a big insert may create a table expansion, and it will cost the number of simple inserts proportional to the number of elements in the table. So that n is what we are counting. Okay, so typically what happens, see, remember when we did an expensive operation in our binary increment, the charges would have come down, right? Because you did 0, 1, 1, 1, 1 and you move them all into 1, 0, 0, 0. So lots of ones have become 0, so the charge is almost vanished. Now it has to build up charge before the next expensive operation, right? And who's going to give you that extra charge? The subsequent increment operations, right? The increment counter. After an expensive, to get that far, I'm going to, new guys who are coming to increment are going to bring that little extra charge eventually for this rich guy to use, right? So somehow 3 is an idea given here. So let's say at this point there is no charge, okay? Because some expensive operation has happened, charges all vanished, and then now increments are happening. Each one is going to come with a unit of 3 units. How do you want to use that 3 units?
1 for insertion.
1 for insertion, okay.
And 2 units on the, not 2 units on the same element,
Okay.
1 unit on this element and 1 on the.
Pick your buddy and give it to him, right, or her. So I'm using 1 for the actual insertion of that element. Then I have 2 units left. I'll put a charge of 1 here, and I will pick a partner here and give 1 for you. Why do I have to give it to that person? Because later on, when the table expands, I need to pay for that insertion, right? And because at this point there is no charge, nobody has a charge. So now all these guys are coming. By the time you finish this table and expensive operation happens, everybody has a charge. You can use that to pay for it. And we'll be back to the square one where table will look like this with no charges here. And the next n by 2 insertions, each one will come with 3 units of charge. 1 for paying for that insertion, 1 for here, 1 for this. You can think in terms of 2 here. So what is the potential of the data set? So let me write some notation here.
Number of elements in the second half. Twice the number of elements in the second half.
So let's call this is the number of elements in the table. And size of P would be the table size, number of locations in the table, right? This is basically the table. Then my charge on the table, how much charge is there? Yes, it is.
Twice the number of elements in the second half.
Twice the number of insertions.
Twice the number of, what is second half, first half? I mean, for simplicity, I drew the picture like this, but you remember that they can all be distributed. Your hashing might have distributed some elements here. All we know is that some half the entries are empty. Okay. No, but you're there. I mean, that's correct. So twice the, how much is it? Twice. 2 into num t minus size t by 2, right? This is exactly what I said. What is num t minus num t is the number of elements in the table, right? But I want to subtract half the table size. Right? This is the extra elements which are sitting there beyond half the table size. Num t minus size t by 2 is the extra elements beyond half of the table sitting there because they all brought 3 units, 1 to pay for them and 2 credits up. Right? So this is exactly 2 times the number of elements in the table. And remember, one sanity check we should do is to make sure the potential we define is always greater than or equal to 0. Because that's assumed everywhere, and when we did this summation amortized cost gives an upper bound for the actual cost, we use this factor. So is it true that potential is greater than or equal to 0? Because remember we assumed that our load factor, I wrote down here, the goal is that the empty spots is less than or equal to half the table. So let me define this. Alpha t is the load factor, which is the number of elements in the table by size of the table. I want always this to be greater than or equal to half. Because one of the goals was to avoid wastage of space. So that means in my table should be at least half full all the time. Right? This I want to ensure, and I ensure it all the time. So because of this is greater than or equal to 0. Right? Always. So now let's go back to our game of computing the amortized cost of insertion using this potential. And it should come out to be what? It should come out to be 3, right? Because that's what we analyzed through a different method. But now using this potential method, let's compute that. What is the amortized cost? There are 2 types of insertion. Easy insert, which doesn't cause table expansion, and difficult insert, which causes a table expansion. Let's do 2 cases. If it's an easy insert, right, no expansion, then what is the amortized cost? Remember, what is the formula? The actual cost plus the potential difference. So what is actual cost? 1, because it's an easy insert, just one insertion I'm doing. And what happens to the potential difference? Table doesn't change, but the number of elements increases by 1. So what happens to the potential difference? This is the potential. 2 into number of elements minus the table size. Table size doesn't change, so they cancel out. 2 into number of elements changes, so what is the potential? 2. It increases by 2. So it's 2. Okay. Let's look at the expensive operation. Okay, what does expensive operation mean? The table expands. So let's say this is the ith operation. So then what is the number of elements after a ith insertion, right? Let's capture these things. After the ith insertion, how many elements are there? Ith. Okay, that's easy. And this is I minus 1. But after the ith insertion, what happens to the table size?
Double the size. Why is the size of 2 minus?
2 times
Size.
size of ti minus 1 because we have expanded it. Okay. So now let's just go plug it into my potential difference and see what is the amortized cost. So this expensive thing, what will be the actual cost? No, not 1. Table is expanded. I. Right? Because there are I minus 1 elements there, you create a table, insert all the I minus 1 plus insert this also. So the actual cost is I. Now let's see what happens to the potential difference. So let me just plug it in. 2 Ti minus size Ti minus we also know what is size Ti minus 1. I minus 1, exactly, right? Table was full, that's why I expanded it. So now go simplify, do whatever. So what do we get? Let's see. Ti minus 1 is just 1, so that gives you I plus 2 when I just use this. And what happens to the size? Less size Ti minus 1 minus size Ti. Right, so this is 2 into I minus 2, right? Because size Ti minus 1 is this. So, yeah, so everything should actually cancel out and what do you get? You get that? Size Ti minus 1. Oh, sorry, yeah, 2 into I minus 1, right? So it's 2i minus 2, so that 2 will cancel out that I in this I. You get 1, is it? Hmm? 3. Okay, unless I made some mistake. So number of elements in Ti after the ith insertion is I. Size of Ti is twice whatever it was, I minus 1. I minus 1, this is I minus 1. So the actual cost of insertion is I, plus I used this 2 num Ti minus I Ti. Okay. So this is 2 plus size Ti minus 1 minus size Ti. So this is okay, right. So that is 2 minus I minus 1, right? So that's actually 3. Okay. Well, that's what we expect anyway. No, the reason I wasn't expecting this is. Oh, right. Okay. No, I thought everybody has a charge to pay for it, so it should be 0. No, this guy is being inserted, so it's the same old game. It's 3. Okay, good. So, I mean, thankfully, in these examples, we have a big picture. We have an aggregate analysis, which gave us an idea of the potential, and somehow we can see it. But I keep telling that soon we will get into some complex territory where some magic potential will work. We don't know why it works, but we will define a potential and plug it into this formula and we'll get an amortized cost. Especially when you get to split rates. But this is nice, right? So it tells you, when the charge is empty, and so, so many guys have to come and provide this charge. So we are distributing this expensive cost to all these insertions, right? When the table expands, there is a big cost, but that is distributed into the insertion that is coming before. Okay. Now, like we did decrement, I was talking about, what if I also do deletions? So I'm doing insertions and deletions, and suppose I still want to maintain this. Will the amortized cost, what happens to the amortized cost?
Similar to that case, we can here also arrive at a sequence of operations such that it's always expensive.
Okay, like what would be the sequence?
Like,
So I'm not sure they're hearing. So what she's saying is similar to the increment-decrement operation. We could come up with the sequence where after some initial point, everything becomes expensive. So what would be such a sequence?
The binary thing, it was like flipping all the zeros and then all the.
Yeah, so something like that. Right.
here like I minus one, say we are going to insert an element where when I minus 1 is power of 2, and then after we keep deleting and inserting. So
The size of the table does not change.
No,
Right?
no, I want to make sure this happens, right?
this happens. So
How do I ensure this? How do I ensure this so suppose the table was like this. So I did some insertion, expanded it, and it is sort of half full. Now I have to tell you what happens if the table goes below. Then one strategy is to decrease the size of the table, because I want to make sure I don't waste too much empty space. Right? So if you have deleted something, let's say suppose my strategy is go to a table of half the size. Seems like a natural symmetric thing.
maybe because there is a greater than or equal to what I say might not work. If it is strictly greater than half, then it's fine. Because even if we remove the element, it's still half full.
No,
So we can
wait. No, suppose I inserted it and table became like exactly half full. That's what happens when you actually insert it, right? If there are 7 elements, it's full. Now you insert the 8th element, you get a table of size 16, and you insert 8 elements.
No, we have 8 elements, and when we insert the 9th element, we go for the next
So you're saying we always keep strictly more than half.
Huh.
Okay. But it doesn't matter. Let's delete 2 elements maybe after that, right?
Okay, yeah.
So if you delete 2 elements, then it becomes less than half. You shrink it. Then I insert a couple of elements, and then you delete a couple of elements. So I can keep doing it, and each one will become an expensive operation. Okay. And why is this happening? Because we want to space out expensive operations, right? That's why we want to space out expensive operations by some cheap operations, so that who pay for the expensive operation. Here, the expensive operation is happening immediately. So one idea is, suppose I won't shrink it moment it becomes less than half. If my goal is to keep it some constant fraction full, let's say I allow myself a load factor of 1/4. Okay. So when the table becomes full, I will get double the space and insert like what I did before. But when the table's load factor goes, this is what is called load factor. When the load factor goes less than half, I don't immediately shrink it. I allow it to go up to 1/4 and then shrink it. That will be an expensive operation. But who's going to pay for those expensive operations? So the load factor was half, charge was not there, they're all cleared. I delete an element, I won't shrink anything. It will be a cheap delete. I delete an element. I allow the load factor to go up to 1/4 and then I am going to shrink it. At that time I have to copy all the elements. Who is going to pay for those copying these elements?
The deletion
The one,
operation should pay.
yeah, the 1/4 deletion that have happened, right? That is enough. That is just still a fraction of the elements. So they all come with some charges to for the subsequent delete elements. Okay. So now let's look at the picture and see what should be the charge and what should be the potential. Right. Now we have two different kinds of potential. If the load factor is greater than or equal to half, and otherwise if it's less than half. Right. So let's keep this. So this part of thing is fine. That after I've done a table expansion, my table is half full. Now all these elements that are coming are going to come with the charge of 3 units, one to pay for that insertion, one on here and one for one of its buddies, so that when the table expansion happens again, there is a charge. Now let's say I do deletion. So I'm now allowing my table size to go to 1/4 of the table. Number of elements to go up to 1/4 of the table size. So now if I delete an element here, how much charge should it come with? 2. Why? 1 to pay for its deletion and
for the copying.
Copying whom?
Sorry,
I'm not even there, so I don't need to copy myself.
Okay, no, for the buddy. Like,
Yeah, so I come with 2 units, one for this pay for the deletion, and one I pick a buddy and say, okay, there is a charge when you will be copied, use it. Right? So literally, I'm not finding a buddy and keeping it, because that guy may actually be deleted also. Right? It's not useful. But think of it as the overall charge in the structure. Okay, you might as well, yeah. So that is the overall charge in the structure. Okay, if that guy is deleted, somebody else will use it. So now I'm going to say, so that's the charging argument, right? Let's now see what should be the potential, right? If the load factor is greater than or equal to half, I'm going to use this potential. What should be the potential if the load factor is less than half? So if the load factor is less than half, how much charge is there in the structure? Whatever guys who have deleted basically from this half. Right? So what is that number? Can you quantify that? This is table size is exactly opposite of this. Table size minus 2 is this much. Minus
the number of elements.
Whatever is deleted. Right? So whatever is deleted. So what is that? That's the minus the number of elements. So minus the number of elements is actually the deleted. Right? In fact, for a half, I think both will coincide. Let's check. And why is this greater than or equal to 0? Oh, because we assumed alpha t is less than or equal to half. What is alpha t? My definition is the number of elements in the table by size of the table. So this ratio is less than or equal to half, would mean that that is greater than or equal to 0. Okay. Okay, so again the idea, the intuition is that you don't want expensive operations to come very often. So if when I'm deleting, I don't want to shrink it immediately. I allow enough number of deletes, 1/4 of these elements, then they pay for this expensive deletes, whatever is left. So that's the idea. Okay, so now you just have to plug it into our formula. Now there are lots of cases, right? There is this cheap insert, expensive insert. Wow, it's a nice commercial way. Cheap insert, expensive insert, cheap delete, expensive delete, and your insert causes the load factor to increase, to go from here to here. Your delete may actually cause the load factor to go from here to here. There are all these cases you have to do. So let me just do maybe a couple of cases, and the rest are all some exercise you can work it out. So if then we have already analyzed the same potential of this we already analyzed, so I'm not going to do this again, right? Because this is we did as part of the insertion amortized analysis. So let's just do, suppose alpha t is less than half. Oh, what happens when it's equal to half? Both of them are same. Well, if it's equal to half, both should be 0. If alpha t equal to half, what does that mean? That total number of elements is half the size of the table. Right. So these two are the same, so it will be 0. There is no charge. So suppose alpha t is less than or equal to half, and we are doing a deletion. So what is the actual cost? It's a cheap delete, so 1 unit. We just delete that element, we don't have to do anything, no shrinking happening. 1. And what happens to the potential difference? We are in this case, right? Size of table doesn't change, so it cancels out. But number of elements decreases by 1. So the difference would be, it's a minus, so it's plus 1. So this is the actual cost. And this is in this case it's an increase. And this is what we intuitively argued also. Remember, when a delete comes, it should come with 2 credits, one to pay for it and one to give it to somebody. So what happens if it's an expensive delete? So this is that. So what is the actual cost? Yeah, what's the actual cost? Number of elements in the table after the deletion, because they are the guys who you need to be inserted, right? So this is the actual cost. But remember, TI is always after.
So, won't it be before the deletion? Because deletion will also take 1 unit of cost.
Okay, so let's add 1 unit of time. Okay, so 1 plus. Deletion is 1 unit of time. Table is shrunk now. So whatever elements are there after this deletion, they all have to be inserted. Right? This is, yeah. Now, so we are here. So what happens to the potential difference, right? I don't know whether I want to go through this. Plus, let me write this. Size of TI by 2 minus number of TI minus is the potential difference. Number of elements before was 1 more, So let's cancel this and write this as plus 1. Okay, what happens to the size? So what did I tell you? What happens to the size?
It becomes half.
Half of what it was. Right, exactly. Right, because there is only so much elements, and take the whole table and shrink it by half, and the half the elements will get filled. So it will become half of what it was.
And it will be equal to a number of elements after the size will be equal to
Half of again.
no, number of the elements in after deletion.
No, half of them. Half of them. Right? So because what we'll do, this is the whole table. This is the number of elements. We will shrink it by half and capture this. Right? So
So
size of Ti equal to size of Ti minus 1 by 2, because we're going to reduce that. Okay? Number of elements in Ti would be half the table size. So can somebody plug it in and see what happens? So size of Ti by 2 and size of Ti minus 1 by 2 when you subtract it. Size of Ti by 2 and size of Ti minus 1 by 4. So it's minus a quarter of size Ti minus 1. So this I'm going to write it as one plus number of elements in Ti plus 1 for that plus 1 minus size of Ti minus 1 by 4. The size of Ti is half of Ti minus 1. So Ti by 2 is 1/4 of Ti minus 1. So half minus half plus quarter is minus quarter. Okay, good. And what do I expect this to be? 3, right? Again, or something like that.
Getting it to be 2.
Okay. So are we getting there?
Size of Ti minus
No.
1 by 4 is number of elements in Ti. So not Ti.
Oh, I think we're getting. Number of Ti is size of Ti minus, so this is 2 plus size of Ti by 2 minus. Yeah.
Ti itself, no, the size of Ti.
Yeah, they cancel out. Size of Ti is size of Ti minus 1 by 2, so they cancel out. Whew. That was scary. I don't think I want to do any more calculations. But you get an idea, right? So basically, we had some aggregate way of analyzing it. From there, we got this credit, which dictated us what sort of potential we want to come up with. And then you plug it in. So clearly, and as I said, there are more cases here which we have not done, because it's possible that your alpha t was greater than or equal to half, and you deleted and you got into this portion. So you have to use the other potential. And sometimes when you deleted and you are here and you added something and it became alpha t greater than or equal to half. So basically you just do amortized costs. There are like 4-8 different cases. I don't know. Amortized cost of cheap delete, expensive, cheap insertion, expensive insertion, and each of them with the alpha was something before and alpha is something after. You do all these case analysis, plug it in, and it turns out that you can show this. Right? I mean, we expect that to happen because of the way we actually have come up with the potential. Okay, so Okay, so I think I will stop here. I won't start. So, and then I'll send you some problems to practice, and also some exercise on amortized complexity to, make your hands dirty and understand this. And next time we will actually get on to some versions of heap, where the goal is to maintain amortized complexity. Like I said, so far, more or less what we did is we have taken the existing algorithms and done an amortized analysis of the operations. But an alternate goal would be is that can I actually even design data structures if, compromising on the worst case time, if I can achieve a better amortized time, right? So that's what we will take us to. Different data structures, versions of heaps and binary search trees we have seen before. We will look at keeping in mind the amortized complexity. Okay, and this is all from Carmen's book, so nothing new. So if you miss anything, go and refer to it.